physics, the third recitation that we're on. Technically it's week 4. Up here I say week 3 because it's our third. So y'all have a test coming up, and we'll go over chapter 3 and 4 questions. In the multiple choice section of chapter 3, number 8, it says, this is the first one we'll go over. It says, your boat departs from the bank of a river that has a swift current parallel to its banks. So you see this squiggly line going parallel to the bank here. If you want to cross the river in the shortest amount of time, you should direct your boat A, perpendicular to the current, B, upstream, C, downstream, or D, so that it drifts with the current. Right? And so if you go upstream, you're going to be going against the current, and even if you're going this way, your upward velocity, or I guess northward velocity here, would be offset by part of the water's current. If you go down, then your velocity is going to be going in the south direction, right? Which would take away, energy from moving to the opposite side. And drifting with the current, you wouldn't necessarily even get to the other side, right? So here the correct answer is A, to the opposite side of the bank, just directly that way. Note that if you do go directly across, even if you're aiming that way, the current will pull you down because you'll be going with the water, but that'll still get you there in the fastest amount possible. The next question is chapter 3, number 20, and it says, a man stands on the roof of a 15-meter tall building and throws a rock with a velocity of magnitude 30.0 meters per second at an angle theta 33 degrees above the horizontal. You can ignore air resistance. Calculate A, the maximum height above the roof of the building that is reached by the rock. So Y max above the roof. B, the magnitude of the velocity of the rock just before it strikes the ground, so velocity final. And C, the horizontal distance from the base of the building to the point where the rock strikes the ground. So what is the maximum x distance when it goes up and over and lands somewhere over here? We have all of the information here. I drew the figure already. And then you put it into, a list format. So here is what we are given. We know that the acceleration in the y direction is gravity, negative 9.8 meters per second squared. And we set y initial to 15 meters because it's 15 above this ground here. And then over here you see sine equals opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. That's the sine, cosine, tangent values for a triangle, right? We talked about that in our first recitation, so hopefully y'all remember that. And then over here we have the a squared plus b squared equals c squared. Right, so continuing on, we're going to first realize that because this is the velocity is at an angle, we need to use components like we did in our first recitation to find the x and the y components of the initial velocity. So here, right, velocity initial y is equal to, and then we use the sine equation here rearranged over here. So the hypotenuse times the sine of theta equals opposite because y is the up and down one. So if we have, sorry, wrong button. If, extend this line up here, go down over here, we've got this lovely triangle here, and the theta is opposite to this up and down line here, right? So that means that those y on the y-axis one is the opposite, right? So hopefully you'll remember that from the first recitation. So you plug in all the numbers, rearrange it, do all that, and then you'll find that it's this number here, 16.34, that way, and then you do the same for the x direction, which in this case is going to be the adjacent to the theta, the angle. So you use cosine because it has adjacent in it. And you do all that. Yippee. Moving on. And that's just going to set it up so that we can use these values in the later parts here. So first, looking at y max above the roof of the building. So that means that it's not going to be 15 plus whatever top value here we've got, right? So assuming it goes like that, then, you know, at some point, go back. Then, like we said before, right here, that value there, that point here is where that's the maximum height above the roof of the building, and the velocity that is positive turns into negative, which means it goes through velocity equals 0. And that's what we have over here. We have y max is where velocity at y, of the y, in the y direction, I'm sorry, velocity in the y direction, up and down, this component equals 0. So plugging in this equation here, this is a v here, then we have this equation, and this says y max. We rearrange it to get y max by itself, right? So it's this side minus this, and then the whole thing divided by 2a here, and then that whole thing plus y naught, which we know that we're setting y naught equal to 0 because we're starting at this point, and so whatever number we get, it's that much distance above the roof, right? So that's why we're starting with y naught equals 0 instead of y naught equals 15. So that's something that you need to be aware of, the wording of the question and what it's actually asking. For the rest of them, you know, you plug them in as we have before. So velocity at y is going to equal 0, right, from here. And then we already calculated the initial y velocity, so we plug that in from here. And then acceleration, of course, is going to be gravity because this is acceleration in the y direction. So, yeah, because all of it is in the y direction. So that's what we get for that. Then we move on to the final velocity, and so we need to, you know, think about, okay, well, it goes up, reaches this point over here, and then goes over here somewhere and goes kaput, right? And so at some point, this rock is going to land on the ground where y equals 0, right? Where the final y equals this bottom part here, 0. And that means, right, and we have that written out here. So velocity in the y final is where y equals 0. We need to figure out the components and then use the a squared plus b squared equals c squared to figure that out. And that's this equation here, just reworded. So the hypotenuse, which is, let me draw this up a little bit more. Move that over. Great. Right, so this is the hypotenuse right, and that is the velocity final. And then here, this one is the velocity in the y direction. It's not letting me do the whole thing, so I'll just move that over there somehow. Okay, y'all know what that is. There you go. And then down here, of course, is velocity in the x direction. Hopefully that's what I said. Yeah, this one here, velocity in the y direction. This one, velocity in the x direction. Oh my goodness, that's not working. Okay, you know that's together. Right, so then this is c, a, and b, so then c squared equals a squared plus b squared. Take the square root of these two combined, and this is the equation that we're using. So moving on, now we need to figure out what the velocity y final is. And before we do that, I just wanted to note that velocity x final, there's no acceleration in the x direction here. So the velocity x final is the same as velocity x initial. So that means that it's going to be this right here, right? So that we already have, and this should be squared here. And then that should be extended. So then now all we have to do is find velocity y final, which I'm just going to call velocity y. So we use this equation here, which is the same as we used over here, but now we have different values, right? Now we have y equals 0, so we plug that in. Well, we plug that in later. First we, rearrange it, which just means taking the square root of both sides, plugging all the numbers. This is what we get. So then the velocity final is that squared plus 25.16 squared, and the square root of all of that stuff. So that's what we get for that number. And finally, we're going to find the x max, which means the distance from here, that didn't work, to here. Right. So this distance here is the x distance. And we know that the initial x position is at 0. And so looking at this here is the equation that would get us to x, right? But then we find that we have this, or we don't have this, but we need this. We have that. We have that. We don't have that. We have everything except for the time. So we use a different equation to find the time. And this one we're using the y variables because we don't have all of the x variables in this particular, instance. If we had the x variables, it would just be yx final equals y not x, right? Because acceleration in the x direction is non-existent. So then that would cancel out the time anyway, because the a would be 0. So here we rearrange it, right? This is what we get. And then plug in the numbers. Time is, of course, positive. So then that's what we get. And then over here, we, plug it in over here. We say 0, of course, right? Because that's 0. And then, plug in all the numbers and you find that the x distance traveled is 103 meters. So that is that question. Moving on. The next question says, crossing the river 1. This is part 1 out of 2 parts, but we're only looking at part 1. A river flows due south with a speed of 2 meters per second. So here, it's flowing due south, 2 meters per second. A man steers a motorboat across the river, right? But I wrote it as a sailboat. His velocity relative to the water is 4.2 meters per second. So his velocity, the velocity here of the boat relative to the water. That's what this means here. V, B/W, boat, velocity of boat relative to water, is 4.2 meters per second. So what that means is that if this boat has the same exact water molecules around him, which direction is he flowing in regards to those? So not looking at the current pushing him in a certain direction. So he is moving directly perpendicular, right, to the bank, to the shores of the river. But we know that the water is moving south at this distance. So his actual position, once he gets to the other shore, is going to be a combination of the velocity of the boat relative to water and the velocity of the water relative to the earth. So let's finish this question here. The river is 800 meters wide. And A, what is his velocity relative to the earth? Right, so it's looking for this velocity, this dotted line here. So velocity of the boat relative to the earth. And let's see. B, how much time is required for the man to cross the river? So time. And C, how far south of his starting point will he reach the opposite bank? So remember, he's going to end up down here. So it's asking right here, what's this distance? So if we draw this dotted line over here, right, what is this distance here? So this is going to be the change in y, right? Delta y. So first, let's figure out the velocity. Because, of course, this is a lovely triangle, this velocity here is going to be a squared plus b squared equals c squared. So here, we have that written down. Right, of course. I can't remember what this number is here. Hang on. Okay. So, you've got those things. You've got the numbers. You plug them in, and then you'll end up with a value of well, I think that is a 1.65 here. And, well, I guess I can just calculate it really quickly. Please hold. Let's see, 2 times 2 plus 4.2 times 4.2 equals 21.64. And what is the square root of that? It is 4.65. So my notes got a little messed up here. This is a 4.65. Glad I checked. Yeah, 1.65 didn't seem right. Okay, so then you've got this, the magnitude. It also asks for the direction. So we take the tangent of theta equals opposite over adjacent. Opposite is the velocity of the water relative to the earth, right? This one here. And then boat versus water is the adjacent one to the angle, because this here is the angle, right? So then you take the antitangent of both sides. You find that theta equals the antitangent of this, and that's the answer. Yay! Moving on to find time. We'll say, okay, we have the distance traveled, that's 800 meters. So we will use the distance equation here. We cross out all the ones that are at 0. And we see that it is x equals velocity naught times t. Rearrange it, and here, plug in the numbers here. And then you'll find that what you get is 190 seconds. Great. And then finally, we're looking at the change in y, so we use the distance equation again. Cross out all the ones that are not applicable. Again, we're left with virtually the same thing, but now we don't have to rearrange it, because what we want is y. Plug in t that we just found, and you'll find that you get 380 meters. Moving on, we have 2 questions left. Almost there. Chapter 4, question 11. A dock worker applies a constant force, a horizontal force, of 80 newtons to a block of ice on a smooth horizontal floor. The frictional force is negligible. The block starts from rest and moves 11 meters in the first 5 seconds. What is the mass of the block of ice? Right, so we have written out all of this information. We've got 80, and this is supposed to be 0.0 newtons. Remember that newtons is kilograms times meters per second squared. We have this lovely figure here. It's a very tall and skinny guy with a small head. Pardon my poor drawing skills. And we are wanting to know what is his mass. Or, I'm sorry, not his mass. What is the mass of the block of ice? So this one here. So what we're going to look at is we have the sum of the forces is mass times acceleration, right here. So this means sum. Force equals mass times acceleration. That's kind of the general term that you've probably heard in high school or just in passing. The sum of the forces, the sum is going to be more applicable whenever you have multiple forces, of course, acting on something. Now, in this case, it said that the frictional force is negligible, so we don't need to worry about that, right? We can pretend that that doesn't exist. And so we have the force, right, 80 newtons. We need the mass, and we need to find the acceleration to find the mass. So, acceleration, we have time and distance, and initial velocity, of course, because it starts from rest. We know that in order to go from rest to moving so many meters in so many seconds, it's got to have an acceleration. So we use all of this equation, cross out what will lead us to 0, of course. And then rearrange it, right? So we have 2 times x over t squared equals acceleration, all that point, right? So this is a 0.88 meters per second squared. Now we rearrange this equation over here, and you'll find that the mass, after plugging in the numbers, is 90.9 kilograms. Remember, the significant figures, this one has 3, it's supposed to have 3, that's a 0.0 at the end. This one has 3, right? And so we end with 3. This number actually goes on and on. Like many of the other numbers, I'm sure y'all have experienced some finicky significant digits in your homework problems. But yeah. Anyway, that was a tangent. Moving on to the last question. It's about an elevator. So, it says, you walk into an elevator. Oh, wait, before I start this. Right, of course, this is my picture of an elevator, and this is the camera that's always in the elevator, saying, I'm always watching you, Wazowski. So I hope that can, brighten up your studies a little bit. Anyway, this question. You walk into an elevator, step onto a scale, and push the down button to go directly from the 10th floor to the 1st floor. You also recall that your weight is 625 newtons. Start each of the following parts with a free body diagram. That's what it says. I did not do that, obviously. But we can draw them out as we continue this. A. If the elevator has an initial acceleration of magnitude 2.50 meters per second squared, what does the scale read? And then B. What does the scale read after the elevator reaches its final speed as it heads to the bottom floor? So A, it's asking, okay, so the acceleration here is negative 2.50. And whenever you jump onto an elevator, if it goes up, you feel like you're forced into the floor of the elevator, right? And if it goes down, then you feel a little bit lighter at the beginning. But then at the end, as it slows down, you always feel heavier. Well, use this to remember that the acceleration that is apparent, that you feel, right, or that the scale reads, is the gravity minus the acceleration of the elevator. So in this case, we have negative 9.9. And this is assuming you're taking the negative scales. Well, I mean, it works either way, actually. So as long as your if gravity is negative and going down and the elevator is going down, then make sure that acceleration is negative. If you say that gravity is a positive number and the elevator is going up, then you have to make the upward acceleration negative. But it's easier to just remember gravity is always negative. It's going down. And then set the likewise accelerations the same way, according to the same polarities. So, right, first we look, weight is 625 newtons equals, of course, mass times gravity. Mass times acceleration equals the force of weight, of normal weight, the regular, general, earthly weight. And so then, dividing this by gravity, you get mass equals this. The scale is mass times the acceleration apparent equals the force going downwards. You include those numbers here, right, of course. So then in this case, the apparent is it's negative 7.30, right? Or I say 0 just because, but we can delete that. So the apparent acceleration is negative 7.3, right? Because it's this one minus that one. And so putting that in here, putting the mass in there, this is the number you get. B, it says, oh, right, and for the free body diagram, you just, here, you can have a box going down is mass times gravity. And, of course, downwards is also the acceleration. And so this is the generic, free body diagram that it's asking for. Yeah, and there's no force going upwards, so you're good. Moving on over here. B, as the elevator reaches the bottom, the elevator slows down, right? So then the acceleration of the elevator approaches 0, right? So as something slows down, acceleration decreases, it approaches 0. As that acceleration here approaches 0, then the acceleration apparent grows closer and closer to the gravity, which means you just put gravity's weight in, gravity's magnitude in for this equation here, or this equation here, right, which is just the same, mass times acceleration. And you'll find the actual weight of the person. So the scale shows the actual weight. Again, like I said in my message, I will be in recitation in case you have questions that you want to, that you need to ask, or if you just want to come. You have no lab tomorrow, so there's no need to come as long as you have liked the message. And yeah, good luck on your tests. Goodbye.